Last thing before we break into just kind of an open session, this is another project that McKinstry did, I want to say 2019. Much smaller project than the Tico Elementary project we looked at a few weeks back, but this is the City of Clay Elum at their water treatment plant. This building was essentially a big concrete box. I don't have a great shot of the overall view of it from up above, but just imagine a big concrete box like this. And then in the middle of the room are a bunch of water tanks and pipes and pumps and all sorts of stuff going on in there. So this is what it looked like before. Some more before pictures. This gives you a little bit better view of a higher angle shot. When we got there, all they had to heat this space was 3 electric heaters that looked just like that. And that style of electric heater is really not designed to be heating a space like this, meaning big open space with a lot of concrete. And concrete is it's a pretty good thermal battery. Concrete will absorb a lot of heat before it'll finally start heating up the room. And these little fan forced electric heaters, so all that's in that thing is a fan and an electric heating coil, so it'll suck in air through the back and then just blow out hot air from the top. That's not a good use for that type of heater, not in this kind of space. And not surprisingly, when we got there, the owners said, hey, these heaters just cannot keep this space warm. We're trying to keep it at like 60, 65 degrees Fahrenheit. On a cold winter day, these things are only maintaining 50 degrees. They also had this huge overhead door. It's kind of hard to see in this angle, but there's a big overhead door right there. That's also a source of a lot of heat loss. So every time they would open that door, all of the warm air that they've heated in a space is just going to be lost out of there. And I think out of frame right here, there may have been a second door down below that's out of shot. Before we talk about what we did, we're going to talk more generally about radiant systems. One reason I thought this was a good project to talk about is the system type that we used here is not one that I normally talk about in the course. So this gives you a little more exposure to something new. So radiant systems. So thinking back to the fundamentals, if our room is hot, we put in cold air. If our room's cold, we put in hot air. That's generally speaking how HVAC works, probably 95% of the time. The exception to this is with radiant heating and cooling systems. Radiant systems don't move air, and they instead heat and cool a space through radiant heat transfer. It's right there in the name. With the idea being, if I put this really hot or this really cold thing in a room, you as an occupant in that building are going to feel cold or hot just by being near that thing. So one example is if you've ever had to sit next to a very old single pane window, which has a terrible insulating value. Even if the room is being maintained at a comfortable temperature, the fact that you're sitting next to that window, which is going to be very cold in the winter, you're going to feel a radiant cooling effect. And that window is essentially going to be sucking heat off of your body. Or conversely, if you are standing next to something that's really warm, like if you're in the kitchen and you turn on a burner on the stove, if that burner is on full heat, you can feel the warmth just by being near that thing, even though there's no air movement associated with it. In HVAC, Radiant systems are not that common, but that might change with some of the newer technologies. An important note with radiant systems, when we've talked about HVAC so far, we've talked about how our fresh ventilation air is typically delivered through the air handling unit itself. And you have to run those fans all the time to make sure you're always delivering that ventilation air. Because radiant systems aren't moving any air, you have to provide ventilation through a separate standalone system, which would be called a dedicated outside air system. And we'll talk a bit more about that in the second half of the semester. Or you could do natural ventilation, which is a fancy way of saying that the people in that space are going to open a window. So this is what we installed out at that water treatment plant. So this is a radiant tube heater. And maybe if you've spent time in shops or commercial garages or things like that, maybe you've seen these before. This big box on the end is our combustion air intake, which would be this duct connection on the top. So we're going to pull in combustion air. We're going to feed the unit natural gas through this connection on the back. And then within this box, we're going to have a combustion process. So as we combust that gas, the hot combustion gases are going to move down this tube. And then there's this reflector that sits over the tube, which is this cut sheet or cut view right here, that does a very good job of reflecting that heat downward, because that's where you want the heat. You want it to come down towards the occupants at the ground level. And then finally out at the other end, so your flue gases move along this tube, radiating heat all the way down. And then by the time they get out here, we need to then get rid of those flue gases. Just like any other combustion process, we need to get rid of that stuff. At Elum, we installed a number of these heaters. It's kind of hard to see the background image on this, but the blue line is our building footprint, and this is looking at it from up above. So we have our gas-fired infrared heaters, and we put them all around the perimeter of the building. And to do this, we had to bring in a new gas service. This building did not have any gas service when we got there, which is why they were using those electric heaters to try and heat the space. So as part of this project, we called Pacific Power, who provided natural gas to the area, and said, hey, we got this customer, they want gas at their building. What'll it take to do that? And if I remember right, Pacific Power basically did that on their dime. We didn't have to pay them to do that. From their perspective, hey, you want to use gas and you want to buy gas from us? That's great. And you want to reduce your electricity use? Even better. I mentioned we sort of put these around the perimeter. One exception to that is down here in this area. There are two crane rails that run on the long sides of this rectangle that we had to keep clear. You really can't put these heaters below that crane, because along those two rails, you're going to be moving that crane back and forth. So we had to kind of thread the needle a little bit to be just outside the crane, but then there was other stuff in the building right here that we also had to make sure we were staying clear of. Here's what one of those heaters looked like installed out at the plant, so we can identify all the parts and pieces. We have our combustion air intake. We have our gas line in, which is coming from this. So this is steel pipe, which goes all the way back to the meter, and then they usually do this flexible connection. This quick little side note on the design side, this little T here on the bottom, This is what's called a sediment trap, also known as a dirt leg. Anytime you have a gas fired piece of equipment, you're supposed to have a little uh, capped off T like that to collect any dirt that could have been carried along with the natural gas, because natural gas isn't completely clean as it gets to your building. This is not actually installed correctly. I can't see one that is in this shot, but I asked them to change it. But basically, you're supposed to force a change in direction of the gas. So what should have happened is the gas should have come horizontally, and then you have a T with this on the bottom, but then it should be going up and then coming to the heater, so that you force a change in direction of the gas, which will make that dirt kind of fall in the bottom of that trap. So quick side digression. We have our combustion, or our burner box where the magic happens, our burner tube that goes all the way down the length of the heater, and then finally at the end we have our flue gases leaving the building. Here's a shot of the outside perimeter, so you can see a bank of these heaters all the way down. Here's a picture of that crane that we had to stay clear of, because that crane it spans these two rails and then can move in any position all the way down. We also had a bunch of pipes on this side, so we had to thread our heaters in between those two things and find room for them. So infrared heaters, these are really nice, but on paper they're really not any more efficient than your basic fan forced gas heater, if you're looking at the combustion efficiency. If that's your only metric, they're not really any better. It's not like infrared heat is 95% efficient or anything like that, which I need to do another quick side digression on. Well, why would we use these then? Most thermostats control their heating systems to maintain some dry bulb temperature of the room. So if you want your room at 70 degrees Fahrenheit, that heater will cycle on and off as needed to keep the room at 70 degrees dry bulb temperature. And for your basic HVAC system, that's fine. 99% of HVAC systems, that's all they're doing. There is something else though called operative temperature. And the short version of what that means is, what does it feel like in the space? The most common example would be if you look at the weather and you see, well, it's 20 degrees outside, and that would be our dry bulb temperature. But with the wind chill, it feels like 5 degrees. So that 5 degrees, that would be the operative temperature. What does it feel like as you're walking in that environment? The operative temperature is based on a number of things. Dry bulb temperature of the room, I mean, that's one of the big factors of how you're going to feel in that room. But it also depends on the relative humidity of the room. More humid spaces tend to feel warmer, even if it's the same dry bulb temperature. It can depend on the air movement speed. So if you have an air forced heater that's blowing air in a room, and that's circulating air, moving air, that air velocity against your skin will impact the comfort of how you feel. The clothing level of the people in the space, that can make a difference. So if you're in a office environment or you're in a warehouse, people can be wearing different levels of clothing. Or maybe if you're in a relaxed office environment, maybe in the summer you are wearing shorts, and in the winter you're wearing jeans. So that can impact the operative temperature. The metabolic level, which is just a fancy way of saying, are you moving around or are you being stationary? An obvious example would be an exercise studio. If you have 10 people exercising in a small space, that's going to have a very different effect on the comfort of the room and the comfort of the people, as opposed to an office building with 10 people sitting at desks. And the last major thing is, what's the temperature of the things all around you? So the example I used before, the single pane window on a cold day, the temperature of that window being cold is going to impact your comfort in that space. And this last point of the temperature of the things around you, this is the big one with regard to infrared heaters. On this project, our infrared heaters were able to save energy by essentially heating objects in the room. They are not heating the air in the room, or at least that's not their primary heat transfer mechanism. So what those radiant heaters do is they're just super hot tubes in the space. They radiate all of that heat into the room, which then hits all of the objects in the room. So at this water treatment plant, that's hitting all of the concrete floors, all of the pipe that's in that room, and the walls and the stairs. That's all being heated up directly by these radiant systems. And what that means is when they open those big overhead doors, now they're not just having this rush of heated air that's just being lost, because it's a lot harder for those warm objects in the room to lose their heat energy just because a door was open for a couple minutes. And when I say heated, I'm not talking about like they are hot to the touch or anything like that, but they are going to be much warmer as compared to a standard fan forced system that is just heating the air and just trying to maintain that air temperature. We are also able to heat our space to a lower space temperature, or I should say dry bulb temperature, for the same operative temperature. So we can make the room feel warmer than it actually is because we're raising all of the we're raising the temperature of all the objects in the room. And so now, instead of maintaining the space at 65 degrees, maybe we can maintain it at 60 degrees dry bulb, and it's going to feel the same for the people in that room. We're also going to save some fan energy. Those old electric heaters we took out, granted, those weren't very large fans. Like I said, those heaters were really not selected for the right purpose, and they weren't very large fans. But these new infrared heaters, they don't have that fan energy because they're not moving air. So there is some energy savings there. We also saved cost on this project by going from an electric heating source to a gas heating source. So we saved energy, and even if the BTUs were the same in the end, by going to a gas heating source, we're cutting the price to about 33% just from that fuel switch alone. The only downside to these infrared heaters are there really isn't an electric equivalent, at least not at this size, not at this magnitude of heater. So now, and more and more, now we're seeing some owners who are saying, I don't want gas in my building. I want to go to electric sources. That's becoming more and more common. And if that's the case, infrared heaters just aren't going to work. So that's the only potential downside. But if you have a building that has gas, or a customer who's okay using gas, which most of them are, then this is an awesome way to heat a big, large open space like this water treatment plant, or something like a warehouse or a shop or something like that. To close this out, this was all about radiant heat so far, but there are radiant cooling systems. These are the ones that are much less common. A radiant cooling system, you are basically running chilled water piping through your slab. So running through these pipes, you would have about 55-degree water through this concrete slab, which is then going to cool that slab down. And then by the nature of that concrete being cool, that's going to draw heat out of the space. So as the occupants in that building, they walk over that concrete slab, they're going to feel that cooling effect just by nature of being close to this cool concrete. Now, this is a lot more involved and not something that can be easily retrofitted, because really this has to be routed in the foundation itself within that concrete. So unless you have a significant renovation project where you are tearing out the floor, it's probably not going to happen. But it is kind of a cool technology. We have this at our McKinstry building, and seems to work pretty well. The only downside is you do have to be careful about cracking the concrete, because it, like I said before, concrete is a pretty good thermal battery, and if you try to impart large temperature swings in a short amount of time, you can end up cracking the concrete. And that's especially true if you have a parallel piping system that's also running hot water, which is something else we have at our building. And so in the winter months, we are heating this slab with hot water, which gives a radiant heating effect. And then in the summer, we're running the chilled water for a radiant cooling effect.